Okay, so let's look at an example. Determine whether the following circles are orthogonal. So the first circle is the circle with the equation x squared plus y squared minus 4x minus 4y plus 7 is equal to 0. And the second circle is the circle with the equation x squared plus y squared plus 2x minus 8y plus 5 is equal to 0. And so we will use the previous theorem. So first we'll calculate the sum of products F1 times F2 plus G1 times G2. So we have negative 4 times 2 plus negative 4 times negative 8. And so this is negative 8 plus 32, which is 24. So now we'll calculate 2 times the sum H1 plus H2. So that's 2 times 7 plus 5, which is 2 times 12, which is 24. So since these two quantities are equal from the previous theorem, we can conclude that C1 and C2 are orthogonal. So as an exercise, determine whether the following circles are orthogonal. So the first circle is the circle with the equation x squared plus y squared plus 3x minus 6y plus 5 is equal to 0. And the second circle is the circle with the equation 3x squared plus 3y squared plus 4x plus y minus 15 is equal to 0. Okay, so new theorem. Let C1 and C2 be circles with equations x squared plus y squared plus f sub 1 times x plus g sub 1 times y plus h sub 1 is equal to 0, and x squared plus y squared plus f sub 2 times x plus g sub 2 times y plus h sub 2 is equal to 0. So let these be circles that intersect at two distinct points which we'll call P and Q. Then the line and all circles except for C2 that pass through the points P and Q have an equation of the form x squared plus y squared plus f sub 1 times x plus g sub 1 times y plus h sub 1 plus k times the quantity x squared plus y squared plus f sub 2 times x plus g sub 2 times y plus h sub 2 is equal to 0 for some number k. Now, if that number k is not equal to -1, this equation is one of the circles, and if k is equal to -1, this is the equation of the line. So this theorem states that if we have 2 points of intersection for 2 circles, then there is a family of circles plus a line that also pass through the points P and Q, and that family of circles on the line all have equations of this form, which is the first circle plus k times the second circle is equal to 0. So proof: let the point P be the point x sub 1, y sub 1. Then, since the point P is on both circles, C1 and C2, we have that x sub 1 squared plus y sub 1 squared plus f sub 1 times x plus g sub 1 times y plus h sub 1 is equal to 0, and x sub 1 squared plus y sub 1 squared plus f sub 2 times x sub 1 plus g sub 2 times y sub 1 plus h sub 2 is equal to 0. And so if we plug this into the equation, we have x sub 1 squared plus y sub 1 squared plus f sub 1 times x plus g sub 1 times y sub 1. That's x sub 1. It's a specific point. Plus h sub 1 plus k times the quantity x sub 1 squared plus y sub 1 squared plus f sub 2 times x sub 1 plus g sub 2 times y sub 1 plus h sub 2 is equal to 0 plus k times 0, which is 0. That is, the point P satisfies the equation C1 plus k times C2 is equal to 0. Similarly, the point Q, which we can denote as x sub 2, y sub 2, is also on both circles C1 and C2. And so this point, Q, also satisfies the equation C1 plus k C2 is equal to 0. And so this equation, C1 plus k C2, passes through the points P and Q. So let's now expand this equation in terms of the constant k. So expanding the equation, C1 plus k times C2 is equal to 0. We have the quantity 1 plus k times x squared plus the quantity 1 plus k times y squared plus the quantity f sub 1 plus k times f sub 2 times x plus the quantity g sub 1 plus k times g sub 2 times y plus the quantity h sub 1 plus k times h sub 2 is all equal to 0. So we consider two cases. Either k is not equal to -1 or k is equal to -1. So first, let's suppose that k is not equal to -1. Then 1 plus k is not equal to 0. And so we divide the equation C1 plus k times C2 is equal to 0 by the quantity 1 plus k to obtain a new equation, which is x squared plus y squared plus the quantity f sub 1 plus k times f sub 2 all over 1 plus k times x plus the quantity g1 plus k g2 over 1 plus k times y plus the quantity h sub 1 plus k times h sub 2 all over 1 plus k. And this is all equal to 0. This is an equation of the form x squared plus y squared plus sum f times x plus sum g times y plus sum constant h is equal to 0. That is, if k is not equal to -1, then the equation C1 plus k times C2 is equal to 0 is a circle. And that circle passes through the points P and Q. So now suppose that k is equal to -1, then the equation C1 plus k times C2 is equal to 0 becomes 0x squared plus 0y squared plus the quantity f sub 1 minus f sub 2 times x plus the quantity g sub 1 minus g sub 2 times y plus the quantity h sub 1 minus h sub 2 is all equal to 0. This is, I'll say, the equation of the line that passes through P and Q. So therefore, if C1 and C2 intersect at two distinct points, P and Q, then the line and all circles except C sub 2 that passes through P and Q have an equation of the form, oops, C1 plus K times C2 is equal to 0 for some number K where C1 and C2 are given in their as their equations. So let's look at an example. Find the circle that passes through the point 4, 3 and the points of intersection of the circles C1, which is the circle with the equation x squared plus y squared minus 4x minus 4y plus 5 is equal to 0. And the second circle, C2, is the circle with the equation x squared plus y squared plus 2x minus 8y. So that's plus 5. We're going to correct this equation. This is first equation. The constant is a 7. And in the second circle, the constant is a 5. This is the same two circles from the previous example. So in this example, we're trying to find a circle that passes through the points of intersection of two circles in addition to passing through a third point. And since we know that this third point must be on that circle, it must satisfy the equation C1 equals K times C2 is equal to 0. And so let's plug in this point. And so we have x squared, which is 16, plus y squared, which is 9, minus 4 times 4, which is 16, minus 4 times 3, which is 12, plus 7, plus k times the quantity, x squared, which is 16, plus y squared, which is 9, plus 2 times 4, which is 8, minus 8 times 3, which is 24, plus 5 must be equal to 0. So now we need to simplify. 16 minus 16 cancels. 19 and 7 is 16, minus 12 is 4, plus k times. 16 and 9 is 25, minus 24 gives 1, plus 8 gives 9. 9 plus 5 is 14. And so we have that 14 times k is equal to negative 4. So k is equal to negative 4 over 14, which simplifies to negative 2 over 7. And so now we can use the constant k to determine the circle that satisfies these conditions. That passes through the 2 points of intersection of C1 and C2 and through the point 4, 3. So we have the equation x squared plus y squared minus 4x minus 4y plus 7 minus 2 over 7 times the quantity, x squared plus y squared plus 2x minus 8y plus 5 is equal to 0. All right, so x squared minus 2 over 7 x squared gives us 5 over 7 x squared. Y squared minus 2 over 7 y squared gives us 5 over 7 y squared. Negative 4 minus 2 times 2 over 7, so that's going to be 28 minus negative 28 minus 4 all over 7, so that's minus 32 over 7 times x. Negative 4 minus 2 sevenths times 8, so that's going to give us negative 28 plus 16, or 12 over 7 times y. Correction, that's a negative. We have negative 28 plus 16, so it's negative 12 over 7. And finally, we have 7 minus 10 over 7, that's 49 minus 10 over 7, or 39 over 7 is equal to 0. So now we can clear the denominator by multiplying through by 7. And so the equation of the circle that we want is 5x squared plus 5y squared minus 32 times x minus 12 times y plus 39 is equal to 0. So let's both check our work and get a nice visualization using a graphing system. The first circle, C1, is x squared plus y squared minus 4x minus 4y plus 7 is equal to 0. The second circle is x squared plus y squared plus 2x minus 8y plus 5 is equal to 0. Now we want our circle that's going to pass through the points of intersection of C1 and C2 to also pass through the point 4, 3. So let's plot that point. And the circle that we determined using algebra was 5x squared plus 5y squared minus 32x minus 12y plus 39 is equal to 0. And we'll call that circle 3. So notice that indeed the circle that we determined does pass through the point 4, 3 and also through the points of intersection of C1 and C2.